You're most welcome to our tutorial, and it's entitled User-Centric Cell-Free Massive MIMO, From Foundations to Scalable Implementation. And I am Emil Björnsson. I'm today a visiting professor at KTH in Stockholm and also an associate professor at Linköping University in Sweden. And this is going to be done jointly together with my colleague Luca Sanguinetti at the University of Pisa and my postdoc Özlem Tukvedemir. And we have together written this new book, Foundation of User-Centric Cell-Free Massive MIMO, which this tutorial is based on, and you should be able to download a free PDF from this link over here. So when it comes to the outline, I'm going to talk about the cellular communication and massive MIMO, where do we stand and what is that we want to move beyond. And then we're going to have the background and motivation of the cell-free approach, particularly cell-free massive MIMO, and the foundation system model. That is what I'm going to cover, and then later you're going to see the uplink and downlink system operation of a system like this, spatial resource allocation, and we will end with some takeaways and open problems. So starting with talking about cellular communication and massive MIMO. The cellular network paradigm is something that has been around for more than 50 years. So at Bell Systems, they were considering how could we potentially deploy a cellular network to be used for telecommunications. And they started to talk about this in these two papers here from the 1953 and 1960. And then you know that the first generation of cellular networks actually were deployed in the late 70s. But the main idea is that we have a number of access points and they are covering a certain region, and all the users that are in that region are going to be serviced by that access point or base station. And the access points to base station are all connected to some kind of core network that facilitates the services that we need, and that is done over backhaul links, which can either be wireless or wired or some combination thereof. And the benefit of this approach when it comes to like reading this original works is that it enabled the same frequency spectrum to be reused over space. And when there are more users in the network, well, then we can just densify putting up more access points. And initially, the idea was that this access point is going to be used only a fraction of the frequency spectrum, but by making sure that we are reusing the frequencies with a certain pattern, we can make sure that we limit the interference, so it's not limiting us. And we can reduce the power as we put up more access point as well, so we are covering smaller and smaller regions in every case. And what we should remember is that when the cellular networks were proposed, the idea was to use them for voice calls, but that is not the main use case anymore. So here is a graph from the Ericsson Mobility Report this year. It shows the number of exabytes per month that are transferred in the world. So that is a huge number. But the important thing here is to look at the two services of data traffic and voice traffic. You see that the data traffic is growing with 60% annually. And this, of course, varying a bit from year to year, but this is what is going on from 2015 until now. While the voice calls, well, you can see that they are down here. This is the data that they are consuming in our networks, and it is increasing by, say, 1% per year, but it's far down here. So it was several years ago that these two different lines were crossing. So when it comes to these two different types of services, when it comes to voice services, they typically require today 10 to 100 kilobit per second, not more. And if you have a higher data rate that you can deliver to the user, you won't get better service quality. However, when it comes to data services, typically a higher data rate is better. So some applications even require 100 megabit or more, and this is sort of important when it comes to thinking about how cellular networks were designed, because they were designed so that we could make sure that everyone gets enough coverage so that we can support voice services. And then it doesn't matter if you are in the edge of the cell or in the center, you get the same voice quality. However, when it comes to data services, it's a large difference between what you can get at the edge of the cell and in the center. So we will come back to that in a moment, but first just talk about that, okay, if it's a data transmission that is the important thing in the networks of today, how do we measure how good a system is? Well, the data throughput or area throughput that we can have in the cellular network, we can measure it in bits per second per square kilometer that the network can deliver as a whole. And we can divide this up into 3 different terms. So the area throughput is equal to B, which is the bandwidth in hertz, D, which is the number of cells or access point that we have per square kilometer, and this could represent a kind of average cell density. And then SE, that stands for spectral efficiency, so that is the spectral efficiency in every cell, measured in bits per second per hertz per cell. And if you multiply these units together here, you will see that you get the bits per second per square kilometer. So another way of viewing this is by saying that the area throughput is the volume of this rectangular or 3-dimensional object that has the cell density, the spectral efficiency, and the bandwidth here. That also tells us that if we would like to be able to have a higher area throughput in our networks, we have these 3 different dimensions to play with. When it comes to spectral efficiency, we can break it down further. We can say that if we can transmit multiple data streams at the same time and frequency, well, then we should sum up their spectral efficiencies. And some optional spectral efficiency that you can get in a practical system is that if you are using QPSK modulation, well, then every stream that is using that get 2 as the spectral efficiency. You get 4 from 16 QAM, 6 from 64 QAM, and then you can go up to higher modulations. And you can achieve things in between by using channel coding, for example. So the spectral efficiency is then the summation over what you get from this different number of streams. And what is a characterizing factor for cellular networks is that we have a sparse deployment of access points. So they could be in towers like this, or they can be on rooftops. And say here that we have 4 different access points put up at 4 different locations. And here we are showing at different positions on the ground what data rate that the user would get at those different locations. Then we can see that they get a high data rate when you are close to an access point, and then it falls down rather rapidly. And why is that? Well, there's going to be large path loss variations because you have these sparse deployments of access points. And sometimes you're close if you're in the center of the cell, but many cases you are at the edges of the cell, and then you have a large path loss. And if we assume that every user is sort of requesting the same type of service, everyone would like to stream like a Netflix video, so then the users that are in the center of the cell, they will get the data rate they need and more very easily. So they will only be turned on part of the time, and they will anyway get their data, and it's going to be buffered so you don't get any interruptions. But users at the edge of the cell, they need to be turned on simultaneously or continuously so that they can get the service that they need. So there's definitely this bias towards having users at the edge of the cell because they are turned on more part of the time, and the area at the edge of the cell is also much larger than the area in the center. And at the edges, you get regular service interruptions when you get to be blocked or things like that. And another characteristic factor of a cellular network with this type of access point is that the base stations, since they are far away, they need to transmit with high power. They need to be very visible, so they have a good chance of seeing over different obstacles in the propagation environment. So it's suitable for coverage. And that was the idea from the beginning, to cover the entire world with wireless voice service. But it's not suitable if you would like to try to deliver some kind of uniform data service quality everywhere, which is sort of what we are as users are requesting for the future. So one option to try to improve the cellular networks, and I was mentioning that before, is to try to densify. And to some extent, that is what we definitely have been seeing over the last decades. So if the base stations or access points were like 10 kilometers away from each other initially, well, nowadays they are more like a few hundred meters away from each other. The problem is that when we're densifying, we go from having, say, 4 peaks here when we have 4 access points, and then we see that at most locations you get much worse performance than you have when you are in the center of the cell. Then if we densify, so here we have like 64 access points instead of 4, well, you see that we have more peaks and we have more centers of the cells, but we also have a lot of locations that are still at the edges of the cells. So we are now going to be limited both by the signal power and the interference that we have at the edge of the cell. And it actually gets worse and worse as you are densifying. You can see that the path flow exponent is going to be smaller, and therefore there are more access points around you that can interfere with your communications. And we are then, by densifying, and I would say we already have reached that point, that densification is not providing any large gains anymore. And the small access point that we could put up in a densified network, they typically don't have the ability to reject interference by using antenna technologies. And most users get mediocre performance. So this is definitely not a way in order to deliver a uniformly good service to everyone. In 5G, massive MIMO have instead been the big thing in order to provide better performance in our networks. So what is massive MIMO about? Well, the idea is that every access point, instead of being a small one with a few antennas or having a passive transmission, passive radiation field, it has multiple small radios and antennas that are integrating with each other, and they allow you to transmit adaptive signal beams to multiple users at the same time and frequency. And the characteristic factor of a massive MIMO system, where MIMO stands for multiple input, multiple output, it's that we say that we in the network have L access point, each equipped with N antennas. They are used to serve many users at the same time and frequency. Each user is served by only one of the access point, and that one is sort of beam forming towards the user. So we have beams within the cell, and then we have interference that's going to leak from other cells. And there is no information exchanged between the access point in a network like this, so you're sort of protecting your own cell against interference. And with this many antennas, every user sees a beam forming gain, which means that you get a stronger signal at the user. And then we also have this multiplexing gain, that multiple users can be served at the same time or frequency. So in the situations today in the networks where you are limited by the fact that multiple users would like to share the base station at the same time, well, now they can do that without getting a large penalty and having to take turns. And when we say beam forming, for example, when it comes to massive MIMO, people might picture it as having an array here connected to some digital signal processor that is sending an angular beam in a particular direction. But that is only how it's going to look like when we are sending a beam to a user that we are seeing in line of sight. In non-line of sight scenarios, then the signal is dominated by a large number of differing scattering paths. And then the beam forming to one particular point in space might more look like the blue case here, where it doesn't look like from the transmitter side that there is a clear directivity of the transmitted signal, but it will still come from multiple reflected or scattered paths to the user in a coherent manner and thereby increase the received signal power. And the massive MIMO base station that are now used in 5G, essentially all of the 1 million 5G base stations that exist now are making use of massive MIMO in the 3.5 GHz band. And they are typically having 64 antennas, sometimes 32 antennas are utilized instead, but I would say that massive MIMO in 5G is characterized by 64 antenna integrated radios. And we have the capability of serving up to 8 or more users. And of course, not always the case. And we use them in mid and high bands. And if you would like to know more about massive MIMO of the conventional cellular type, you can read our book, Massive MIMO Networks, which you can download for free from massivemimobook.com. So how does massive MIMO work? So I'm going to tell you sort of that in a nutshell, just so you see how we are building upon that when we build another type of cell-free massive MIMO later on. So we know that the channels in a wireless system are going to change both in time and in frequency. However, we can always find a time interval, let's call it TC, seconds, where the channel is going to be roughly static. We call that the coherence time of channel. So it's fixed at a time. And over the frequency domain, because of the multipath propagation, we're also going to have variations in the channel. And we can say, however, that for a particular bandwidth, BC, hertz, called the coherence bandwidth, the channel is going to be fixed in the frequency domain. So if we design our communication based on that, we can have a so-called coherence block spanned by the coherence bandwidth and the coherence time that contains TC times BC samples. And these are sort of channel uses, number of times we can transmit while having a fixed channel. And this is what we do in Massive MIMO system, particularly when we operate them in TDD, called the time division duplex, where we are in a coherence block like this, sending uplink and downlink data, and we are sending pilots from the users to the base station in order to learn the channels. So the operation in general then is that in a TDD operation, we send uplink pilots. Each user transmit one so-called pilot signal, which is a known signal, so that the receiver observes the known signal over an unknown channel and can learn that unknown channel. And then when we know that, then we can send uplink data. So each user is transmitting that data. The access point decodes it. And now since it knows the channel, it gets unknown data over a known channel. And that is also possible to decode. And then we can switch to downlink and transmit beamformed signals using the same channel knowledge that we obtained from these pilots, because within one coherence block, the channel is the same in the uplink and the downlink. So the access points are beamforming those signals over the channel, and then we can protect ourselves against interference using this beamforming. So what are then the expected gains from the cellular kinds of massive MIMO that we are seeing now in 5G? Well, if this was the situation before, then massive MIMO is taking us to the right path here. And this is still focusing on one user. So users are going to benefit from the beamforming gain, which means that at any point here, except in the center where you sort of are saturated, you are going to get a higher data rate here than you got here. And in addition to that, we can have multiple parallel data streams, which gives us the possibility to serve multiple users at the same time. So we are more protecting ourselves against being congested in the network. But there are still large problems that remains, because we put these antennas still at sparse locations up in tower somewhere. So there are large sync to noise ratio or SNR variations, and that's what you see here. Yeah, the worst case situation might be a bit better, but you still have large losses. And there's still going to be interference between the cells because, yeah, even if we call it massive MIMO, there's a large number of antennas, say 64 of them. In the 5G implementation, we typically take them as 8 by 8, so it's a rectangular or square array. And even if there's a large number of antennas, in every dimension, there is only a small number of them. 8 by 8 is a small, each of the numbers, but 64 is large. So that sort of tells us that we still don't have a super good ability to protect ourselves against interference unless we are in the ideal situations. So what are then the potential evolutions of cellular and massive MIMO beyond 5G? Well, what we could do is to go from having these kind of co-located arrays that we have on rooftops, for example, which are sending beams, into sort of having much larger, physically large arrays. Not having a large number of antennas in a small box, but having an even larger number of antennas in a much larger box, so even spread out here with larger antenna distances over the facade of a building. This is what we can, for example, call an extremely large aperture array. And since it's physically large, we have the ability of still separating users. Now we can separate the users much better. We can handle interference better. And we will also see some kind of near-field behaviors where we can separate users not only based on the angular directions of them, but also the depth. However, since we are still putting all the antennas at one location, sort of a facade like this, we still are going to have large SNR variations. We're still going to be sensitive against blocking. If you put up the hand in front of the phone, if the signal's only coming from one direction, well, then that will block the signals. And we still are going to have cell edge issues where the users are far away from this array and we still don't have the ability to cancel interference. So cellular Massive MIMO will evolve, and you can read much more about that in our paper, Massive MIMO is Reality, What is Next? But we will look at another way of evolving the MIMO technology in this presentation. Because our ambition is to go from this situation here with the Massive MIMO, where we have better performance than in the past, but still large variations, to a scenario where it's probably unavoidable to have some variations in the performance, but we would like those variations to be small and making sure that we have an almost uniformly high data rate wherever you are as a user at every location. Your data rate that you get on that location is going to be high. So how can we achieve this? Is it even possible? Well, we sort of need to deal with two things. We need to deal with the signal to noise ratio variations by sort of densifying the network somehow, and at the same time deal with interference. So that brings us to the second part of this presentation, the background and motivation of cell-free Massive MIMO. So what we would like to do is a paradigm shift. From the scenario, traditionally when we have these access points in elevated places surrounded by users, to a situation where we have a user that is surrounded by a lot of antennas that can be more at the street level and that is serving the users. So we would like to get rid of the situation where we have cells, where if you are at the edge of the cell, you have bad performance, and where you have large variations. So there's going to be no cell interference, it's going to be much smaller SNR variations. Of course, you can't be close to all of the antennas that we put up. Well, you will at least be close to some of them that are in your neighborhood. And since the signal can now come from access point located in different directions, you're going to have a macro diversity towards blocking. So if you hold your phone and block its signal from one direction, well, then signals can come from other directions instead. And in principle, each user is going to be served by all antennas, at least all antennas that can reach it with a signal that is stronger than the noise floor. So this is what we call cell-free networks. And the way of implementing this is to make use of some kind of central processing units. So there is essentially 3 levels in this architecture. We have the access points. It's these here. And a user that is somewhere here can then be served by the access point in this neighborhood. Then these access points are connected to what we call central processing units, or CPUs, and sometimes these things are also called edge clouds. So these are computers that are operating together with these access points. And then we have these connections between the access point and the CPUs, which are some kind of wired frontals. And in principle, they can also be wireless, but here we are drawing them as being wired. And then the CPUs, if there are one or multiple ones, they are connected to the core network that is sort of facilitating the different services in our network. And now someone might ask, well, how is this related to how we build networks today when we talk about cloud RAN or centralized RAN or C-RAN in general, because both abbreviations stand for the same thing? Well, this is essentially a cell-free physical layer that can be built on top of that. So C-RAN is just the idea of having multiple access points that are sharing the same sort of edge cloud or central processing unit where some of the baseband processing can be operated. And at an architecture like that, we can build a cell-free network, which tells us that it's not that far into the future that the cell-free paradigm can actually take off. So the philosophy of building something like this to let a user be served on multiple access points is that it allows us to interference reject. So here's an example of this. Say that we have 3 transmitters, the red, the blue, and the green one, and they are transmitting to 3 receivers, the red, the blue, and the green one. And traditionally, if these are like 3 different cells, well then the red receiver here will see the red signal as a desired one, and then it will see two interfering signals. So if you model this entire thing as a so-called interference channel, then all these three receivers will be in the following situation. It makes one observation, it has one desired signal inside that observation, and then it has two interfering signals that are added to it. And those signals are sort of three unknown signals, but just one operation, one observation. And that is too few in order to actually deal with interference. So we are interference limited in a scenario like this. But let's consider the same type of setup, but instead we are connecting the three receivers together, and we let it use all those three receive antennas to decode the signals. Well, then we reach what is called a multi-access channel instead, some kind of uplink scenario, where we have three observations over these three antennas. There are three desired signals, and you know that we can solve an equation system if we have three unknowns and three equations. So we can reject interference in a scenario like this. And the general idea of trying to have cooperation between the receive antennas in the uplink of a system is something that goes back in time. So Aaron Weiner was talking about this already in a paper from 1994, Channel Theoretic Approach to a Gaussian Cellular Multiple Access Channel. So let me provide you with a short historical background of these cell-free technologies that we will then cover in further more detail. So if we look back in time to the beginning of the cellular networks, and maybe until 2000 or 2005 or something like that, sort of the main idea had been that we should avoid interference somehow. So we can, for example, have frequency reuse patterns, so neighboring cells are using different frequencies. We can use sectorization, so within one cell we divide it up into different sectors, and then every sector uses a different part of the frequencies, and then the sectors that are pointing towards each other in neighboring cells also use different frequencies, but we can make sure that the same frequencies are reused in different sectors in the neighboring cells. So these are different types of interference avoidance methods. And there are also these ideas about sort of trying to avoid interference with coding. So this is called successive interference cancellation, or a non-orthogonal multiple access, NOMA, it has also been called recently. This is sort of an old school approach to live with interference and then try to decode it as best as possible. So even if this is something that people are talking about in the context of 4G and 5G networks, it's sort of an old school thing, and there's much better ways of dealing with interference. Namely, the second approach was to spatially interference reject. This was something that was studied to a large extent in 2000 to 2010. Then the idea was, as in Aaron Weiner's works, that we would like to turn the interference channel into a multiple access channel in the uplink and a broadcast channel in the downlink. So it's sort of the idea that underpins Cell-Free Massive MIMO, and it has been given many names. Network MIMO, which is sort of an idea to spread out antennas and let all of them serve all the users. Group cells was an idea to take cells that we have put up, and we are grouping them together into clusters, and then some clusters are serving some users, other clusters serving other users. And there's the name multi-cell cooperative networks, for example. And these were all described as some theoretical ideas about how you could make use of this spatial interference rejection between different access points by sort of turning an interference channel into a multi-access or broadcast channel. Then in sort of the work towards 4G, say from 2005 to 2015, coordinated multipoint was the name that was given to these type of technologies when they tried to put them as an add-on to the 4G standard. And COMP wasn't particularly successful in 4G, and I think there are multiple reasons for that. One is that the 4G standard was built so that it should support both TDD and frequency division duplex, or FDD, and that means that we cannot simplify the protocols, but we need to make sure that the different access points are sharing things like channel state information in between each other, and that makes It's very hard to get good gains without getting too much overhead that is eating up those type of gains. And also the standardization to make sure that this type of methods are working, even if we can use different vendor hardware in our networks and mix them as we like, that didn't turn out to work very well. And we will come back to some other issues around these type of things as well. Cell-Free Massive MIMO is sort of a new name from 2015, which is a restart of the topic, using the methodology of analyzing and building the system for TDD operation from the cellular Massive MIMO literature. And the focus was sort of to start from the beginning to deal with the scalability issue when it comes to implementing something like this in a real network and actually get the gains. And it's also sort of based on the paradigm of not having big base station towers that are cooperating, as was the idea with coordinated multipoint, but instead to have many access points with simple hardware that are spread out around you in an ultra-dense manner, so that you have many more access points and users, and to have sort of an inherently distributed architecture instead of a centralized one. And the name Cell-Free Massive MIMO first appeared in this paper here from 2015 on the Spoke conference. And as you can see, the main idea was to deliver a uniform service quality in the network. So in the Cell-Free Massive MIMO literature, it's hard to find just one distinct definition of what is Cell-Free Massive MIMO and what is not. So here is one possible definition. It is a network with L access points that are jointly serving all the UEs, all the user equipments in the network, where every access point have multiple antennas, N, or at least N is a fairly small number, so it could be 1, but it could be 4 or 8 or something like that, but it's not going to be a large array. And there are many fewer users than their access points. So K is number of users and L was then the number of access point. And the access points are interconnected via some kind of front hall where there can be sharing data and potentially some channel state information with one or multiple central processing units that are then facilitating their cooperation. So a few different ways that one can think about this is that Cell-Free Massive MIMO is a combination of this network MIMO concept from the past in a ultra-dense network where we have many more access point and users. It could also be viewed as a combination of network MIMO, the idea of having distributed antennas that are cooperating, but operating them using the optimized TDD Massive MIMO approach. Or one can view it as taking network MIMO, combine it with CRAN, and additionally add distributed antennas to the system as well. So in a way, it's sort of the intersection between network MIMO, the way of operating transmission in cellular Massive MIMO, and the sort of ultra-dense deployment. So let me then continue by demonstrating some of the main benefits if we compare it with the cellular network. And we will compare 3 different things. A cellular Massive MIMO system, or it's actually just one cell here, but it have many antennas. Then a small cell system with 64 single antenna access points on a square grid like this, and here we have 64 antennas at this access point. And the same kind of architecture at the small cell here, the same location on the access point, but now they are all cooperating in a cell-free manner. And these are simulation areas of 400 by 400 meters, but it is not the main importance here what kind of simulation parameters that we're using. But we will see that between these 3 different scenarios, there are differences in what SNRs we are getting and in what kind of interference rejection capabilities that we're having. So cell-free benefit number 1 is that we have higher SNR with smaller variations. So what we can see here is a sync-to-noise ratio that users are getting. And what we are doing is that we take our one user and we are dropping it at one random location in that cell area that I was showing you. And some parameters, we have like 10 dBm transmit power, we have a noise power that is sort of for 10 megahertz of bandwidth, and we have a typical 3GPP like path loss model, or we can also call it the channel gain at different distances d. And the solid black curve here is showing you what kind of SNR variation that we get with the cellular massive MIMO system. So it's just one base station with 64 antennas. And we see that there are large variations. So the lucky users will be up here, but most of them will be down here at the edge of the cell. Then we can see that if we build a cellular network based on small cells, we get a red curve here, smaller variations, but they still exist, and it's preferable for most of the users, but not for the best ones, or the one that is lucky. And then we have the cell-free system, the blue curve here, which is equally good as small cell for the best users, but still outperformed by cellular massive MIMO in that case, but they are better for the worst user. So if we are talking about the 95% likely performance, the one that we can deliver to 95% of the users, then we look at this curve here, and we see that we can have large improvements by going to the cell-free scenario. When we look at just this first benefit, you might get the impression that, well, do we really need to go from small cells to cell-free if the gains are only this small? Well, let's now drop multiple users in the same area. So now we have 8 randomly located users, and we're operating the system as before, and we are sort of associating the users with the best access points. And what you can see now is that the black and the blue curve for cellular massive MIMO and cell-free, they are roughly the same as before. They were moved a little bit downwards, particularly the cell-free case was lost a little bit down here, but the cellular case with small cells is dropping a lot from being very close. So if I go back one slide, you see that they were close here, and then you can see when I go to the next page that it was moving very far to the left. So the small cell system is no longer competitive. However, the massive MIMO and the cell-free system are almost unaffected. And one can now argue, well, massive MIMO is still better up here. Yes, nothing can beat standing in the center of the cell and having all the antennas directed right onto you. But in most cases, it is the performance down here that matters. What you get on the average, what you get in the worst cases, like the 95% likely. And here you really have a multifold improvement in SINR. The third benefit is how the signal focusing works like when we have distributed antennas. So if you just put all of your antennas in one array at one location, then the beamforming that we get from a compact array is sort of confine the signal in one angular direction. And that limits our resolution because, okay, signals that are in that angular window cannot be separated. And when the users are far away, as at the edge of the cell, we'll have difficulties of separating users. Beamforming from a distributed array, well, it doesn't create beams. Maybe it's the wrong thing to call it beamforming. We can call it something else, coherent transmission. But what it actually leads to is that we are focusing the signal at one particular point in space. So that is what we are showing here. In order to make it visible, we need to consider a rather small simulation scenario. So we have a array that is distributed like this around the edges of a square. And they are one wavelength apart. So this is 10 wavelengths times 10 wavelengths and 10 wavelengths. Here we have a user at one location, and all of the antennas are transmitting in line of sight towards this user, and they try to focus the signal there. And what we can see then is that we get the strong signal. We up here on the color scale. So 1 is like 100% the strongest signal that we're getting, and then everything else is normalized towards that. And the focusing is in the small region here, which have a length which is like half a wavelength or so. So that is where the signal focusing appears in space and confined in a small region. And this is also saying that, well, since it's not like we are here transmitting in the beam like this, where multiple users that would be along that beam will get interference. Well, here you only see strong interference in the small region around where the user is. So that means we can throw out many more users in this area and deal with interference when we have beam forming from a distributed array. So my part will be wrapped up by talking about the foundations and the system model of Cell-Free Massive MIMO. So some notation that we're going to use for the rest of this tutorial. We have a user. We call the user K. So this is an arbitrary user, and there's user from 1 up to capital K. And access points, AP, they are from 1 up to capital L, and typical number is lowercase l. The channel vector between this user and this access point is HKL. So the channel notation is like this. First we have the user's number, and then we have the access point number. And remember that every access point have n antennas, so the channel in the coherence block is a vector of length n. We will consider in some parts of this tutorial random fading distributions, and then we use what is called correlated Rayleigh fading, where in every coherence block this vector is drawn randomly from a complex Gaussian or complex normal distribution where the mean is 0, and we have a so-called covariance matrix, which in systems like this we typically call a spatial correlation matrix, because this matrix is describing two things. One is what is the average channel gain or path loss from different antennas to the user, and another way is how are the channel coefficients correlate towards each other. And this correlation is something that happens when the antennas are confined in a small volume, because they are sort of seeing partially the same type of scattering objects, and therefore they're seeing similar fading realizations. There's one realization in every coherence block, and well, we're going to need this model later on. I will now define the system model that we're going to use in the uplink. So if you look at one access point L, the received signal that it is getting in the complex baseband is a vector, YL, UL for uplink, so it has length n, and it's going to be a summation over the signal transmitted by different users. So if we're sending a data signal, SI, well, if we assume that it comes from a Gaussian codebook with 0 mean and power pi from user I with power pi, then it's going to propagate over the channel from that user to the access point, HIL. So remember user I, access point L. And then since all the signals are transmitted at the same time and frequency, they are summed up, and then we are adding noise to it. And you see that the noise here have a complex Gaussian distribution. And the basic thing that an access point is doing when it's observing a signal like this is that it will like to make guesses of what the different data signals were. And say that it would like to estimate the signal from user K, SK, then since it observes a vector of length n, but it wants to guess a scalar value, then it needs to somehow take that vector and project it to a scalar. And that is typically done using a linear receiver, and we call this vector VKL as the receive combining vector. It's a vector of length n, and we take the inner product between the received signal and that one. And we should select this one based on some channel knowledge, some knowledge about these channels, and we will see later how we can obtain that. And we should select it so that when we are taking the inner product here, we are getting rid of the interfering signals to some extent, and we are emphasizing the desired signals. And there are some underlying assumptions here, such as that the entire network is synchronized in time and things like that. So we are considering the idealized case, which you could, in principle, achieve with an OFDM system with some extended cycle prefix and things like that. But that is not the main idea or thing we want like to cover in this tutorial. Let's talk briefly about the main principle of how does channel estimation work. If you would like to learn this channel so we can select our receive combining. Well, as I was saying earlier, in order to learn a channel, a user sends a pilot signal, a known signal. Say that it's just one symbol, psi, that we are sending. And then when we are receiving this signal at APL, it goes over the channel from user K, because this user K that is transmitting. Then at the same time, it reaches all of the access point, but we are focusing only on what happens on APL. The access point is receiving the signal over this channel. It gets noise, and this is our received pilot signal or pilot vector that is of length n. And a simple estimate that we can get is to sort of just try to get rid of this pilot signal. So we multiply with the conjugate of it if this is a complex number, and then we are normalizing it. So by multiplying like this, we get rid of this term here, and we only get the channel by itself here, and then we get some scaled version of the noise. This is called least square estimate. This is a simple way of learning the channel. And importantly, for one user, it only needs to send one pilot in order for all of the access points to observe the signal, and then all of them can do an operation like this at the same time. However, in a big network, think about that we're going to put up a network over an entire city with thousands of users. Well, then every user cannot have their own pilot, so they will have to share somehow. So typically we restrict the number of pilots that we have in our system. We call them, say, tau p, and then that is the number of pilots that the users are sharing, and some of them are going to use the same one, and some are not. Let's now shift to the downlink and talk about the system model that we have in that case. The received complex baseband signal at the user K is a scalar because we assume it has one antenna, and what it's going to contain is, remember this was the channel from access point L to the user, and then if access point L is sending a vector signal over it an antenna that we call XL, well then we take the inner product between that transmitted signal and the channel. We add it up from different access points because all of them are transmitting at the same time. We add a scalar noise signal that's complex Gaussian, have a particular variance, and that is a received signal. And if the access points are now going to transmit to multiple users at the same time and sort of direct the signal with beams towards the users with their multiple antennas, then you can of course do this even if you have only one antenna. The data transmission at access point L was this XL vector. And in this one, we would like to sort of squeeze in the signals, the data signals meant for different users. So if we call sigma I here as a data signal meant for user I, then we assume that it's a complex Gaussian codebook. And here we have normalized the variance to 1. And then how strong the signal is to this user is determined by the vector WIL that is used to take the sigma I signal and map it into a vector. And when we do that, that's when we are beam forming. We are determining how strong the signal is going to be and in which direction we're going to transmit it. So we call this vector the precoding vector, that access point L is assigned into user I. We will cover both the uplink and the downlink in more detail later, but right now let's take a pause and look at what we have described. Because every access point serves all the K users, which means that it must estimate the channel to K of them. Then they're going to use those estimates to compute the combining and precoding vectors for all K users. And in the downlink, it needs to get the data for all K users. In the uplink, it needs to compute those K local estimates of the datas. And then in order to cooperate with the different access points around them, it needs to sort of send those data estimates to some other place over the front haul. And all these type of things are scaling with the number of users. So it's not scalable to a large network where we are serving many users. And for example, if we let K goes to infinity, it won't work. So that is a scalability issue that we need to solve if we should ever be able to design and implement the cell-free network. So let's make the following assumption. Every access point have a local processor. And we should limit the complexity per access point so that we can add additional access points, serve additional use in our network, but we don't need to upgrade what every access point is doing. So here's a definition of a scalable operation. A cell-free network is scalable if the computational complexity and frontal signaling per access point remains finite as the number of users go to infinity. And then in reality, we'll never have an infinite number of users, but still, this is sort of a way of showing that a method is fundamentally scalable or not. So, of course, the scalability issue of building a large cell-free network is something that people have been talking about in the past. And the way of trying to deal with such a problem in 4G with the coordinated multipoint approach was a network-centric clustering, where the neighboring access point formed a fixed cluster. So it's from the network perspective. And for example, we have the green cluster here, and all the users in the green cluster are served by all of the access points in that region. Then we have the purple cluster and the same thing there, and so on. And the problem with this is that many users are at the edges of the clusters. So this is not a cell-free approach. It's just sort of merging some of the access points together, but not all of them. Many users will still be at edges of now clusters and not edges of cells. What we are looking for is a way of clustering together and limiting how many access points serves each user while still having a cell-free operation. And for that to happen, we need to take a user-centric clustering. We need for every user to let it appoint which access point that should be serving it, based on which one are actually reaching it with signals. So the red user here is served by these 4 access points. The yellow user have selected these ones, the purple user has selected these ones, and so on. And we see that some access points are in common between users and some are not. And that is sort of a characteristic of a cell-free network. So for every user, you're still seeing or getting the impression that all of the surrounding access points are actually serving me, and that's why we can retain the cell-free philosophy, even if not every access point in the entire world are going to solve you naturally. And to put this into our system model, we will make use of something called dynamic cooperation clusters, which was a concept that I proposed almost a decade ago. It was a general framework that enables unified analysis of everything from interference channels to ideal network MIMO, and cell-free networks, as we are going to describe them, is somewhere in between. So the way that I will now try to show how to solve the scalability issue is to look at this definition of scalability again and see that it's all about what happens to the complexity and the frontal signaling when the number of users goes to infinity. And now remember that I said earlier that we need to limit how many pilots that are in the network, because every user cannot have an orthogonal pilot. Tau p was the number of pilots, and we are assuming that we are somehow associating them with users in such a way that we are able to control interference in the pilot transmissions. And even if the number of users is very large, tau p remains finite. And that is the solution that we're going to utilize here, that every access point is serving at most tau p users, one having each of the different pilots. And that makes a good sense, because if multiple users are using the same pilot, you cannot really separate them. So from that perspective, it's rather natural that you are limiting your operation like that. So based on this tau p pilot, the access point is computing one estimate for each of them. So at most tau p estimates. And then based on those estimates, it's computing combining and precoding vectors. That's also tau p of them. So all of these type of things that has to do with complexity and frontal signaling will be proportional to tau p. And by assumption, tau p is not going to infinity. So that is sort of solving the scalability, but can we still get a cell-free like operation? Well, that is sort of moved over now to how we assign the pilots, and that needs to be done in order to enable a user-centric network. And here is one access-based algorithm for how to assign the pilots to the users in a user-centric manner and still do it in a distributed way, so we don't need to consider the entire networks as a whole. This is something from this paper, Scalable Cell-Free Massive MIMO Systems. It's based on the idea that they are already used in a network when the new user joins. That user, in step 1, selects one access point, the one with the best channel, and then it appoints that access point as its master AP. Then in step 2, we are letting that access point select the pilot. So it's monitoring all of the tau p pilots. It selects the one where it hears the least interference, and it assigns that one to the user. So that is sort of locally the best pilot. And then it invites other surrounding access points to join in serving the user. And some of them will join, some won't. And that is sort of creating this user cluster that you're seeing here in a user-centric manner. So it's sort of inviting all of the surrounding access points to serve the user. Now I will show you how we can put these dynamic operation clusters into the system models that I already have described. So say that user K is served by access points with indices in a set MK. So this is a subset of 1 to L, the indices of those access points that is serving the user. Then in the uplink, APL estimates the signal SK during the data transmission. And I showed you earlier that it takes a received signal and it computes an inner product with the combining vector that it's computing. Now it will only do that if L is in the set of access points serving this user. Otherwise, we assign 0 to it when it's not in that set. And one way of compactly describing both of these cases without having a lot of different cases in all of our derivations is to assign a matrix DKL. This matrix is an identity matrix if the access point is serving the user and 0 otherwise. And then we just insert it in between here so that we are getting this expression when we are serving the user and 0 otherwise. In the downlink, we can do the same thing. The APL transmits the signal XL, and it's a summation of all the users. Here we have the transmission from before, the precoding vector, the data signal. And then we insert the same matrix here, DIL for user I and access point L. And that means that DIL-WIL is sort of together a joint effective precoding vector. And it's either equal to the original one or 0, depending on if you are serving the user or not from this access point. So with that, I'm done with my part of this tutorial, and I hand over to Luca Sanguinetti, who is going to consider the uplink and downlink in more detail.
Hi everyone, thank you for watching our tutorial. My name is Luca Sanguinetti. I'm a professor at the University of Pisa in Italy, and I'm going to cover the second part of the tutorial, which is about the uplink operation of the user-centric cell-free massive MIMO network. So, as you know, the analysis of any communication technology needs a channel model, a proper channel model that can reflect the main characteristics of the technology. So I will start introducing you the channel model that we have used in the book and the one that we're going to use in this tutorial for the analysis of cell-free network. So a very common stochastic channel model for the analysis of multiple antenna communication techniques is the uncorrelated radiofading channel, which is valid for no line of sight communications under rich scattering. Under this model, the channel vector between access point L and user K is assumed to be Gaussian distributed with zero mean and covariance matrix given by the identity matrix scaled by the large scale fading coefficient. Now, the main drawback of this model is that spatial correlation is neglected. By assuming a covariance matrix equal to the identity matrix means that the antennas are spatially uncorrelated and the spatial directions are all equally important. This is not the case in practical networks where spatial correlation naturally appears. For this reason, in the book, we use the correlated radiofading channel model where the channel vector is still Gaussian distributed, but now the covariance matrix is a full matrix given by the spatial correlation matrix between the access point and the UE. And this matrix can be used for modeling the spatial characteristics of the channel. Similar to the uncorrelated model, we define the large-scale fading coefficients as the mean of the diagonal elements of the correlation matrix, which can be different. They have not to be the same as in the case of the uncorrelated radiofading channel model. So this is the model for the channel vector between the UE and the access point. We need to statistically model the collective channel, which is basically the vector collecting all the channel vectors from the UE to all the access points in the network. By taking into account that the access points will be geographically distributed with a distance much bigger than wavelength, we can assume that the collective channel has a structure like that, where the spatial correlation matrix is a block diagonal matrix, which means that the channel vectors of the different axis points are independently distributed. So the analysis in the book is valid for any arbitrary correlation matrix. We assume to use a particular one, which comes from the assumption of a uniform linear rate at each axis point. This is motivated by the observation that in cell networks, the axis points will have a small size and probably a small number of antennas. So we can reasonably assume that they are displaced over a uniform linear rate. If we assume that all the multiple components arrive from the far field of the array, we can compute the generic element of the correlation matrix in this way, where beta is the common large-scale fading coefficient, and phi and theta are basically the azimuth and elevation angle, where this is the probability density function of the two. Now, the numerical integration of this integral can be performed numerically for any probability density function. We assume a local scattering model, which allows to model the probability density function according to this joint Gaussian distribution, where the variances are called the angular standard deviations for the azimuth and elevation angles. To study the impact of the spatial correlation in the network, we can, for example, study the eigenvalues of the channel vector, the correlation matrix. So assume, for example, to have 8 antennas at an axis point. So in this plot, we plot the eigenvalues for the uncorrelated really fading case, where all the eigenvalues are equal, and for the case where the angular standard deviations are 20 degrees, 15 degrees, and 5 degrees. So as you can see, the eigenvalues are widely different when the angle spread deviations is small, and the angle spread decreases with an increasing angular standard deviation. For example, in the case where we have an angular deviation of 5 degrees, the first four eigenvalues contribute to all the energy of the channel. This means that the spatial correlation matrix is almost rank deficient, and all the channel realization will be a linear combination of the first eigenvectors of the correlation matrix. Now, we should notice that the spatial correlation has a huge impact in conventional cellular networks, conventional cellular massive MIMO networks, because of the large number of antennas, and the large variations can be used for mitigating the interference in the network. In a cell-free massive MIMO network, we do not envision the same large number of antennas per access point, so we can probably not be able to make efficient use of the spatial correlation properties of the channel as we can do in a cellular massive MIMO network. Despite this, however, spatial correlation will have an impact on the performance of the system. So we have a model for the spatial correlation matrix. We need a model for the large-scale fading coefficient. We assume that the access points operate in an urban environment and serve a very dense population of user equipments. They're 10 meters above the plane where the users are located. So according to these definitions, assumptions, we assume that the large-scale fading coefficient in dB is given by this formula here, where this is a fixed coefficient. That's the three-dimensional distance between access point L and user K, and this is the shadow fading term from between access point L and user K, which is assumed to be log normal distributed. with these statistical properties, which mean that if you consider two different access points, the shadow fading terms are uncorrelated because the access points will be far away in space. On the other hand, if you consider the same access points, the shadow fading coefficients will be correlated if the UEs are closely located in space. So now that we are equipped with a channel model, we can start evaluating the performance of the network in the uplink. First of all, that's the network that we're going to consider. Cell-free network with many access points geographically distributed in the coverage area, many single antenna user terminals distributed in the coverage area. So the first problem to solve is the channel estimation problem. To perform coherent processing between the access points and across the operating access points, each access point needs to estimate the channel vector for all the users is serving. Since we assume a block fading channel model, the channels need to be estimated once per coherence block because they change from one coherence block to the other in an independent way. So to do that, we assume a TDD protocol where we have a training phase which is composed by tau p samples, and this training phase is reserved for uplink pilot signaling. So this uplink pilot signaling can be used by the mobile terminal to transmit a pilot sequence that spans tau p samples. Each access point will use the received signals to estimate the corresponding channel. Ideally, we want to all the users use orthogonal pilots such that the interference in the network can be removed. Now, since we have only tau p samples for the training phase, we can only have tau p mutually orthogonal pilot sequences. This means that we cannot assign orthogonal pilots to all the users, since the number of users will be much larger than tau p. This will give rise to the pilot contamination problem. Okay, let's denote with phi1, phi tau p the pilot sequences. We assume that tau tk is the index of the pilot assigned to user k, and we denote by pk the set of users using the same pilot of user k. So at the receiver side, the access point that wants to estimate the channel of user k, first of all, must remove the interference from the users using orthogonal pilots. And this is done by multiplying the received signal by the pilot sequence assigned to the user of interest. So in this case, we can remove the contribution of the users using the orthogonal pilots. So we are left with the desired channel and the interference from the pilot sharing UEs. So the users using the same pilot of the user of interest. And then we have the noise. So the problem is to estimate the channel by using this observation vector. So very common way is to use the MMSE channel estimation scheme, according to which the channel estimate is obtained in this way, where this is the observation vector. There is the inverse of a matrix, which is the correlation matrix of the observation vector, which is a function of the spatial correlation matrices of the pilot sharing UEs. And finally, we have here the spatial correlation matrix of the user of interest. An interesting consequence of the MSC channel estimation scheme is that the estimation error are independent. With Gaussian distribution, with Gaussian distributions where CK is the error correlation matrix. Why this is an interesting observation? It's an interesting observation which can be used for computing the spectral efficiency of the network. So the MMSE channel estimation scheme is optimal whenever we have full statistical knowledge of the channel. This knowledge here is used for computing the correlation matrix of the observation vector, and is also used here for the channel of interest. So if this knowledge is not available, we should resort to different channel estimation schemes. So the alternative channel estimation schemes are the least square channel estimation scheme or the element-wise MSE channel estimation schemes. They provide larger mean square error, so they have lower estimation accuracy of the MSE estimator, but can be used whenever the complexity is an issue, because the complexity of the MSE is proportional to the number of antennas, or whenever we have incomplete knowledge of the statistics. Now, these channel schemes are of interest in cellular massive MIMO systems. Why? Because a large number of antennas is used in that case. But in cell-free massive MIMO, they are not very much interesting because N is small. So we envision to use a very small number of antennas per access point, which means that these two channel estimation schemes are not very much important. Now, I mentioned the pilot contamination problem. The pilot contamination problem is a consequence of the fact that users cannot use orthogonal pilots in the network. So the first consequence of the pilot contamination problem is the reduced channel estimation quality. The other consequence is that the channel estimates becomes correlated. And this, as in cellular massive MIMO, makes very hard to mitigate interference between UEs that use the same pilot in the uplink and in the downlink. So once we have estimated the channel from the user and the access point, we have to compute the collective estimate of the global channel, because this is needed for coherent processing. Now, the point is that only a subset, only the access points which are serving the user of interest can compute the channel estimates or can send the pilot signals to the CPU, central processing unit. So this means that only the following partial channel estimate of the channel is known in the cell-free network. So basically, we have all the knowledge of the channels of the users that are of the access points that are serving the specific user. Okay, let's try to investigate the impact of the cell-free architecture on the performance of the channel estimation scheme. So we now consider a network with 64 single antenna access points and assume that we consider a single user active in the network. So we compare the estimation accuracy of a cellular massive MIMO network, cell-free network, and a small cell network. So in the cellular massive MIMO case, all the antennas are co-located at the single base station. In the cell-free case, they all cooperate to estimate the channel and serve the user. And in the small cell case, only one small cell is responsible to serve the user of interest. As you can see, the estimation accuracy with massive MIMO is lower. And the small cell is achieving the best accuracy. Why? Because in this case, only the best access point is serving the user of interest. So despite this, If you consider the spectral efficiency of the network, even though the small cell has a better estimation accuracy, if you compare the spectral efficiency by using max version combining, you can see that the cell-free technology achieves better spectral efficiency, especially for the users with bad channel conditions, whenever the user has bad channel conditions. Massive MIMO is achieving the lower spectral efficiency, and the small cell are equally good as the cell-free when the channel conditions are good, but in the case of bad channel conditions, they are outperformed by the cell-free network. So this is the case for a single user. If we consider multiple users, then cell-free is going to improve even more the performance with respect to the small cell implementation. So this will be seen when we consider a more complete network. Finally, I want to investigate the pilot contamination impact. For the same setup, now we have two users using the same pilot. So that's the estimation accuracy of the channel estimation scheme when the interference signal ranges from minus 30 dB to 20 dB. As you can see, the impact is negligible whenever the interference is 10 dB weaker than the noise. However, it's very sensitive whenever the pilot sharing UE is close to the serving access point. So this means that the UEs that an access point serves should use different pilots. That's what we observe here, where we plot the effective signal to noise ratio as a function of the distance of the interfering UE. So as you can see, is larger if we are close to the access point, but above minus 10 dB for hundreds of meters. So this means that the pilot contamination is an issue, as even if the UE is quite far away from the access point. So if we increase the length of the pilot, you're not going to help the performance of the network because the effective SNR increases, but you can we have a less frequent pilot use, which can basically exploit it to reduce the pilot contamination problem. So the point here is that pilots must be assigned properly according to the position of the user in the network. This is why we make use of this pilot assignment and clustering information algorithm, which basically tries to let each access point serve only one user per pilot. So this is the algorithm that Emil has introduced you in the first part of the tutorial. So once we have introduced the channel model and addressed the channel estimation problem, we are now ready to look into the performance of the system in terms of spectral efficiency. We start with the uplink. So to address this point, we need to operate the network. And the network can be operated in two different ways in a cell-free massive MIMO context. So it can be a centralized network, it can be a distributed network. So we start with the most advanced uplink implementation of cell-free, which is a fully centralized network where the access points, they're basically relays that forward the signals to the central processing unit for processing. So this means that each access point sends TLP receive pilot signals to the central processing unit. Each access point sends the received uplink signal to the CPU, and the CPU uses all the signals to perform channel estimation and data detection. So nothing is performed at the access point. The access point, each access point is only forwarding the receipt signal to the CPU, which is taking care of the channel estimation and data detection process. So this is the highest level of cooperation among the access points. So under this operation condition, the estimate of the signal transmitted by user K is given by this formula here, where this is the combining vector used to detect the signal received by access point L. This is the matrix accounting for the access point serving or not serving the user of interest, and this is the receive uplink signal of the access point. So we can use this matrix form here, where BK is the centralized combining vector and Y uplink is the collective data signal, where N is the collective noise vector. Everything is a function of the collective channel vector of each user, and PI is basically the power used for transmitting the data information. Now, we are in a cell-free network which relies on a user-centric approach, and this is done by designing properly the matrices here. So we should take into account that whenever the matrix is zero matrix, this implies that the inner product is zero, which basically means that only the signals from the access points for which the matrix is different from zero will be used for the detection of the signal of the user K. Now, if you consider the CPU as a receiver equipped with L times N antennas, this model is mathematically equivalent to the signal model of an uplink single-cell massive MIMO system with correlated fading. However, there are a few key differences which should be taken into account in the analysis of and design of the system. First of all, the multiple UEs which are served by the CPU can use the same pilot. So we may have pilot contamination between the UEs which are served by the centralized processing unit. This is not normally the case in a single cell massive MIMO network, where pilot contamination does not occur between users in the same cell. The second difference is that the correlation matrix is a block diagonal correlation matrix. Why? Because the channel vectors of the different access points are assumed to be independently distributed. And this is not normally the case in a single cell massive MIMO system. Despite this difference, we can use the analytical results from the massive MIMO literature to compute the spectral efficiency of the network when operating according to centralized approach. So in this case, the spectral efficiency in the uplink is given by this expression here, where the expectation is with respect to the channel estimates, and this is the effective SNR of the communication link, which is given by this expression here, where we have the combining vector, the selection matrix, and finally the estimate of the collective channel vector. Now, by using this expression, which is very similar to what we have in a single cell massive MIMO network, we can compute the optimal combiner, which is given by the MMSE combining vector. This is a consequence of the fact that this singleton SNR is a Rayleigh quotient, which is maximized by the MSC combining vector, which is composed by two parts. One is this part, which is going to maximize the power, the signal power, the signal gain, and this one is going to handle the interference, is going to find a good trade-off between signal power maximization and interference mitigation. Now, this combining scheme is optimal, but as you can see, is a function of all the channel estimates of all the users in the network. So it doesn't scale with the number of users. If you increase the number of users, then increase the complexity of the combining scheme. So it's not scalable according to the definition that we have given about scalable cell-free network. So we need to look for alternative solutions which are scalable, basically independent of the number of active users in the network. So the simplest one is maximum pressure combining, which selects the combining vector in this way. So that's a very simple scheme, which is scalable, independent of the number of users in the network. The key benefit is that, first of all, the combining follows directly from the channel estimates. There is no need to compute any additional computations. However, the performance of the combiner might be poor when you have interference, as expected in a high populated cell-free network. So instead of using this very suboptimal scheme, we can think about an alternative approach, which relies on the observation that most of the interference in a cell-free network will be generated by the UEs located in the neighborhood of the user of interest. So in this case, instead of considering all the users in the network, we can just consider those users that are served by partially the same set of access points of the user of interest. And this set of users is basically given by this set here, which is a function of the selection matrices dk and di. So by using this set, we can think about an alternative scheme, which is called partial MSC combining scheme, which is exactly in the same form of the optimal one, but the sum is not taken over all the users in the network, but just over the users within the set Sk, which is independent of the number of users. And thus, although non-optimal, but only suboptimal, this scheme is scalable. So it's a scalable approximation of the optimal MMSC combined scheme. So we have two scalable combiner, which are scalable with respect to the number of users in the network. Let's try to understand if operating the network in a centralized manner is a scalable or not solution. So in each credence block, if the network is operated in a centralized manner, each access point needs to send all the pilot signals, which are equal to tau p n complex scalars, and then all the received data signal, which is equal to tau u n complex scalars. So if you put together the two, they are independent of the number of users in the network. So the signaling, the frontal signaling is still scalable. if we operate the network in a centralized manner, because I mean, what you have to exchange is not a function of the number of users in the network, but only of the size of the training phase, the uplink data phase, and the number of antennas at the access points. The other knowledge which is needed for operating the network in a centralized manner and to perform MMSC processing, we have to have knowledge of the statistics of the channel. Now, this knowledge can be acquired directly in the CPU. There is no need to exchange this information over the front tool. Why? Because the CPU can use the uplink pilot signals to estimate the statistics of the channels. The situation will be different when we operate the network in a distributed way, because in this case, channel estimation will be performed directly at the access points. So we have a network operating in a centralized fashion, which is scalable with respect to the combining scheme, and is also scalable with respect to the amount of information that we need to exchange over the frontal links. Okay, the alternative way is to operate the network in a distributed fashion. So in this case, instead of sending the pilot and the receive data signals to the CPU, each access point can compute local channel estimates and use the local channel estimates to compute local estimates of the symbols. Exactly in this way, where this is the combiner, the local combiner used at the access point to locally estimate the signal of the user of interest. Once this information is acquired, what the access points can do, they can actually send the local estimates to the CPU, where they are linearly combined for final detection. This stage is called large-scale fading decoding. So in this case, instead of taking a final decision at the access points, the final decision is taken CPU on the basis of the local decisions taken at each access point. Okay, so and to limit the frontal signaling, the access points send only the local estimates. They do not send the channel estimates. So this means that the combining coefficients here, the CPU must be selected according to the statistics of the channels. They cannot be selected according to the instantaneous knowledge of the channels, because the CPU has no knowledge of the channel estimates. The channel estimates are locally computed at the access point and used at the access points for locally estimating the symbols. These local estimates are then combined linearly by using weighting coefficients, which can only be a function of the statistics of the channel, the CPU. Okay, so this stage is called large-scale fading decoding. Now, the objective now for the CPU is to design the combining vector in a way that the performance of the system will be maximized. So we can rewrite the global estimate by taking advantage of the structure of the network in this way, where this is the large-scale fading decoding weight vector over all the access points in the network, and GKI is the collective receive combined channels between user I and all the access points that serve user K. Now observe the GKI. changes in every coherence block. So it's a function of the instantaneous realization of the channels. But remember, the CPU has only statistical knowledge of the channel coefficients. So in the design of the network, we should take into account these constraints. Actually, we can do that in the same way as being done in the cellular massive MIMO literature. And we can, especially in the downlink, so we can compute the spectral efficiency in the uplink when the network is operated according to in a distributed fashion by using similar tools from those in cellular massive MIMO, and this is what we obtain. So that's the spectral efficiency in the uplink when the network is operated in a distributed fashion. Compared to the centralized operation, you can see that everything is a function of the statistics of the channels. It's not a function of the instantaneous channel estimates, realization of the channel, okay? But despite this, we can still optimize the weight vector in the same way we have done in the centralized operation, because this is once again a Rayleigh quotient, and the optimal weight vector is given by this expression, which is very similar to the MSE combining scheme, except for the fact that it's a function of the statistics of the channel. Okay. So if we use this optimal combining vector, the SINR will achieve its maximum value, which is given by this. So we can compute in closed form the maximum value of the effective SNR. In the same way, this can be done for the centralized network. Now, the problem with the optimal large-scale fading decoding scheme is that it's not scalable. Indeed, we need to have statistical knowledge of this matrix here, which is a function of the total number of users in the network. This can be seen here, where similar to the optimal MSE combined scheme, the sum is over all the users in the network. Okay, so we need to reduce the complexity of the scheme such that it can be made scalable with respect to the number of users. In the same way of the optimal MSE combined scheme, we can observe that only the users which are close to the serving access point of the user of interest should be considered, because they are going to create much interference in the network. Now, the simplest solution should be to give equal importance to the local estimates by setting the weighting vector equal to 1. But this is very suboptimal, since it's going to give equal importance to all the access points in the network, even though some of them might be subject to high interference or low signal-to-noise ratio. It can even happen, by using this approach, that an access point can reduce rather than increase the spectral efficiency due to the suboptimal use of the local estimates. So by following the same approach of the partial minimum mean square error combining scheme, we can only consider the users that are partially served by the same access points. So if the access point selection is done properly, these UEs will cause the majority of the interference. So by doing this, we can approximate the optimal vector with a sub-nearly optimal one, where the sum is taken over the users that are partially served by the same access points. So in this case, the number of statistical parameters that need to be exchanged over the frontal is independent of the number of users. So the system is scalable, nearly optimal, and scalable. So we have a scalable, nearly optimal, large-scale fading decoding scheme. What we have to do, we also have to derive a scalable local combiner scheme. The simplest one is the maximum ratio combined scheme, which we know to be scalable. It's only a function of the channel. I mean, it can be computed directly from the channel estimates. Another benefit is that the expectations can be computed analytically. So these are the two major benefits of selecting the combiner according to the maximum ratio criterion. But instead of using this suboptimal scheme, we can actually follow the same approach of the partial MSE combined scheme in the centralized case and think about a local partial MSE combiner, which takes these four. Now the sum is taken over the UEs that are served by access point L. And these UEs are those in the set given by DL. The complexity is still independent of K, which makes this a scalable solution. It's a scalable solution with a lower complexity than the partial MSE. Why? Because now the inverse here must be as a dimension of n by n instead of NL times NL. So the total number of antennas in the network. Now the dimension of the matrix is equal to the number of antennas per access point. Okay, so we have gone through the centralized and decentralized approach. We have scalable and unscalable solution for running the network. Now we are going to measure the performance and compare the performance of the different techniques by using this network configuration. So we have a network area of 1 kilometer per 1 kilometer. It's a square network. The access points are randomly deployed in the network. We assume to have 400 access points or 100 access points, and the number of antennas per access point is 1 or 4. So this means the total number of antennas is fixed and equal to 400. The bandwidth is 20 megahertz. This is the receiver noise power. We assume that the maximum uplink transmit power is 100 milliwatt. The samples per coherence block are 200. That's the channel gain at 1 kilometer. The path loss exponents, we assume that the access points are 10 meters above the plane where the users are located, and this is the standard deviation of the shadow fading. Okay, so these are the parameters that we're going to use here in the uplink, later on in the downlink, and also in the analysis of the scalable power allocation schemes. Okay, so first of all, we consider centralized operation. And we compare the unscalable optimal solution where all the users are served by all the access points. Then we have the unscalable solution using the MC, where we use the dynamic clustering approach. Then we have the partial MC with dynamic clustering approach, and also the maximum ratio combining scheme with dynamic clustering approach. There is also another combining scheme which is inspired by the MC, and is the partial regularized zero forcing approach. So we see that the best one is the centralized network with the optimal MSC combiner, where all the users are served by all the access points. That's the optimal solution, but it's unscalable with respect to number of users. There is a very negligible gap in using the MSC with dynamic clustering, and there is still a very negligible gap by using the partial MSC with the dynamic clustering approach, which is a scalable solution. On the other hand, if you use the max-iteration combining scheme with the dynamic clustering approach, which is a scalable and very simple solution, the performance are not very much competitive. There is a large gap between the optimal scheme and max-iteration combining with dynamic clustering. Now we change the configuration of the network. We have 100 access points and 4 antennas per access point. So the optimal one is still the unscalable solution where all the access points are using MSC combining and serve all the users in the network. But the partial MSC solution with dynamic clustering has a very small gap with the optimal one. And still, the maximum ratio combining scheme is not very much competitive. So this means that we shouldn't use, even though we have a centralized network, we shouldn't use the maximum ratio combining scheme. We can gain a lot by using more advanced techniques, which are still scalable as the maximum ratio combining scheme is. Now, if you compare the configuration with 1 antenna per access point and 4 antennas per access point, you see that the first case is more desirable. So it's better to have many more access points in the network than a less number with a bigger number of antennas per access point. This is true when we operate the network in a centralized fashion. The story will be different for the centralized case. So with a centralized operation, it's much better to have many more access points with single antenna each, instead of having more antennas per access point. Now, the spectral efficiency that we have used is a lower bound to the capacity of the system, which can be computed by using very standard lower bounds, which are very common in the massive MIMO literature, but they're bounds, lower bounds to the capacity of the network when having in perpetuity and treating the interference as noise. So if you want to evaluate how good these bounds are, we can actually compare the spectral efficiency achieved by these bounds with the capacity of a system which has perfect knowledge of the channels. So in this case, as you can see, the partial MSC scheme is very close to the Gini-aided scheme, which means that the spectral efficiency achieved by this scalable algorithm is very representative of the performance of the network. Now we turn into the centralized scheme. So the best solution is given by the local MSC combining scheme using the optimal large-scale feeding decoding approach. But if we can achieve the same spectral efficiency with 3 simplifications. First of all, we can only involve a subset of the access points, which is what we do with the local partial MSC combiner. And then we use the nearly optimal large-scale fading decoding approach. So as you can see, by imposing these three simplifications to achieve a scalable solution, we are on top of the optimal one, which is unscalable with number of users. So these are the performance for a configuration with 400 antenna access points, each with one antenna. So if we consider the other case with 100 access points, each with 4 antennas, the performance are slightly different, but still the scalable solution given by the nearly optimal large-scale fading decoding approach and the local partial MSC combiner are on top of the optimal ones. And if you compare with maximum ratio combining, the gap is huge, as it was in the centralized approach. The same for the other configuration. So this means that, once again, maximum ratio combining shouldn't be used in a cell-free network. It's much better to use more advanced techniques. There is a lot to gain, even though they're still scalable as the simplest one. Finally, I mean, if you compare in the decentralized approach, if you compare the performance between this configuration with 400 access points and this configuration with 100 access points, is better to use this configuration. Why? Because in this way, since we cannot take advantage of the cooperation between the access points, it's better to equip each of them with some degrees of freedom given by the antennas to deal with the interference. So in this case, there is much to gain locally by using multiple antennas at each access point. Finally, we want to compare the performance of the cell-free network with a cellular network. We make the cellular network operate according to a massive MIMO cellular network and according to a small cell network. So for the small cell network, we have 100 cells, exactly as for the cell-free network, but there is no cooperation between the access points. Now, if you compare the performance of the small cell network with the distributed cell-free network and scalable approaches for large-scale fading decoding and local combining, you can see that the cell-free network provides better performance, especially for the users with bad channel conditions, those with a low spectral efficiency. But if you consider the centralized operation, there is much to gain with respect to the small cell configuration. And the gap is even larger compared to massive MIMO. The other observation is that with the user-centric approach, we can provide a more uniform service in the network. This is because the CDF curves are more steeper with respect to the massive MIMO configuration and the small cell configuration. So the cell-free architecture is better in improving the spectral efficiency and providing more uniform service to all the users in the network. Okay, so we have analyzed the performance in terms of spectral efficiency. Now we can analyze the scalability of the different configurations, basically the centralized and decentralized configurations with different combiners. So first of all, let's consider the frontal signaling. Here we have the centralized case. Here we have the decentralized case. The centralized case, in the centralized case, the number of complex scalars is constant. So there is constant with respect to number of users. Why? Because everything is not a function of the number of users. What the access points share over the frontal is proportional to the number of antennas per access point and the number of samples for the training phase and data phase. The same for the distributed approach when you use the dynamic clustering approach. On the other hand, when the distributed network is operated such that all the access points are serving all the users in the network, then the number of scalars increases with the number of users. So with respect to the frontal signaling, we have scalable solution for centralized and distributed approach. Now, in terms of number of complex scalars for the statistics of the channel, here we have the optimal large-scale fading decoding approach, where all the users are served by all the access points. As you can see, this is going to increase with the number of users. With the optimal one, but using a dynamic clustering approach, then the number of complex scalars is also increasing with the number of users. On the other hand, if we use the near optimal large-scale fading decoding algorithm and the dynamic clustering approach, we can actually guarantee a scalable solution with respect to number of users. Why? Because they do not increase as the other two with the number of users. For the computational complexity, that's the computational complexity for the centralized approach. The optimal one has a computational complexity which increases with the number of users. On the other hand, if we consider the partial MSC combiner with dynamic clustering, is even decreasing with the number of users. And this is because we're partially considering only subset of users in the design of the combiner. And the interesting observation is that maximum ratio combining in a network where all the access points are serving all the users can have a higher complexity than more advanced techniques with dynamic clustering. So the major observation here is that don't use maximum ratio combining even if all the access points can serve all the users. Why? Because you can do much better in terms of performance and complexity by using advanced schemes which can select properly the users to deal with. And according to the number of, when we consider distributed implementation, the complexity doesn't grow with the number of users for the local partial MSC combiner. You see, it's a constant one with respect to the number of users, while the other two, which are, the local MSC combiner and the local MSC combiner, where all the access points are serving all the users, is also increasing. Okay. So in the end, we have been able to design a scalable network which performs as good as the unscalable ones in terms of spectral efficiency. And the frontal requirements and complexity of this scalable solution are both scalable with respect to the number of users. Having said that, I'm done for my part. Now, Arslan is going to talk you about the downlink operation of the network. I hope you have enjoyed this part, and I'm happy to take any question. If you have any, you can send me an email whenever you want. I wish you a good day and hope to see you soon. Bye-bye.
Thanks, Luca, and hello, everyone. Now I will continue with the downlink operation. On the left-hand side, you see the received downlink signal at each user K. And it's a summation of the signals corresponding to each access point I. And now there's an additional conjugation operation on the channels just for notational convenience in the downlink operation. So after applying this conjugate transpose operation, this row vector represents the downlink channel from access point L to user K. And the term inside the parentheses is the transmitted signal from access point L. And I is here the user index. And on the right-hand side, you see this is a downlink data signal. And it has unit power. And this NK, last term in the received signal, is the additive Gaussian noise at user K. Now, since each access point is not serving all the users, we use again the dynamic cooperation cluster matrices, these E matrices, to represent effective precoders. As you recall from the previous parts, these dynamic cooperation cluster matrices are either identity or zero. If user I is served by access point L, so in set notation, we use here as this, because here this MI is the set of access point indices serving user I. If L is an element of this set, then user I is served by access point L, and this dynamic cooperation cluster matrix is identity, so the effective precoder just equals the selected precoder based on the channel state information. Otherwise, if user I is not served by access point L, then the dynamic cooperation cluster matrix is zero, so the effective precoder is just zero vector. So that access point L is not transmitting anything to that user I. We can also express this summation by using a summation over user indices I, and we here construct collective channel vector for user K from each access point. And here it starts from 1 to capital L. And also the collective precoder, effective precoder vector here for user I, and again for each access point L. And now defining this collective channel and collective precoder vectors, we can represent the received downlink signal in this form. Now there's an important thing here, because we have the same system model for both centralized and distributed operation. Because each access point transmits some precoded signal, and the received downlink signal is the same for both centralized and distributed operation. But there is an important difference. Now the selection of the collective precoding vectors, this overall vector for each user differs. Because in the centralized operation, these are selected based on the all channel state information for user I collected at the central processing unit, and some interference suppression precoding vectors can be applied in a centralized manner. But for the distributed operation, these overall vectors should be constructed just part by part. For example, for each access point L, this effective precoder is constructed based on the local channel state information. So this is the difference, but we have the same system model. Now we will start with the centralized downlink operation. When we look at the centralized operation and received signal, we see that the design of this effective precoded, overall effective precoded at the central processing unit is just like an L times N antenna single cell massive MIMO system. But there are some differences because each access point is not serving all users, so there are some zero parts in the overall precoded vector. And we have block correlated Rayleigh fading, and also there are per access point power constraints. So unlike single cell massive MIMO, collocated massive MIMO, we have now L different per access point power constraints. And here XL is the transmitted signal from access point L. Here we define it, and it's just from the previous signal part. And now you see the summation over all users, but the effective precoders are either zero or the selected precoder if user I is served by access point L. Now we can obtain the achievable spectral efficiency user K in a closed form for the downlink centralized operation. And you see here the effective SNR. This pre-log factor just represents the ratio of the downlink channel users to the coherence block, the total number of channel users in a coherence block, because some part of it is reserved for uplink operation and also training operation. And here is the effective SNR, this term. And now, since we consider centralized operation, we express the terms using the overall channels from all access points defined in the previous slides, here as HK and WK. Here is the desired signal and the other pre-coded signals coming from other users. So they are interference and the noise power here you see. Now we will look at the duality result between the uplink and downlink operation. Why? Because in the uplink we have obtained optimal combiners. Because the spectral efficiency of user K in the uplink is just affected by the combining vector of itself, user K. But here the situation is different. Now the spectral efficiency of user K is affected by all the transmit precoding vectors, as you see in the previous SNR expression in the denominator. So we have a more complicated precoding selection problem, and there is no closed form optimal result. But we can use uplink-downlink duality theorem to design heuristic precoders in the downlink, inspired by the uplink counterparts. And the duality result just says that, let's denote the overall combining vector and transmit power for user I in the uplink by these terms. And if we select the precoding vectors by normalizing with a corresponding power rho I in the downlink, but using the uplink combining vector structure, then there exists a downlink power allocation policy. We can determine these rho i's satisfying this equality, and then we can obtain the same effective SNRs as in the uplink with the optimal combiners. But this theorem does not say anything about the per access point power constraints, because due to centralized operation, now we have only K power coefficients, because we designed the overall precoding vector, so direction should not be destroyed by different access point power. So we use a common term here. And these rho i's, even we select these rho i's according to this criteria, we may not satisfy per access point power constraints. But this duality result actually constructs a way to design heuristic precoders. We can use the same structure of the optimal combiners from the uplink operation. Now I will continue with the distributed downlink operation. Actually, we have the same achievable spectral efficiency expression. As you remember, we have the same system model, but the only difference is in the selection of the precoding vectors. In the distributed operation, now each access point selects its local precoder vectors based on the local channel state information. So although the spectral efficiency and SNR, effective SNR, has the same form, now due to distributed operation, here we are expressing it using the portions of the overall channels and overall precoding vectors. So now you see this HKL in the original form, not in the overall channel and precoded form. So we have the same spectral efficiency, but again, we can use the duality. Although duality result in the previous slide is valid for centralized operation, you see only there are K power coefficients. Now each access point in the distributed operation can select its power for each user accordingly. So because there is no direction preserving criteria is in the centralized one, but still we can use duality. And inspired by the uplink combining vectors, we can design local transmit precoder design in the distributed operation. Now let's look at the frontal signaling load in the downlink for both centralized and distributed operations. For the centralized operation, the central processing unit sends the transmitted signal from each access point L. It's an n-dimensional complex vector, and here, as you recall from the previous parts, capital N is the number of antennas at each access point L. Because the central processing unit applies the centralized precoder and adjusts the power of each access point L, So it just sends these n-dimensional vectors. And here the number of complex scalars to be shared over the frontal is, with any precoding, irrespective of the precoding, in each coherence block is this number. And tau d is the number of downlink channel users in each coherence block. So actually it has a similar structure as in the uplink, just this tau d differs. In the uplink it's tau u. And also, when it comes to the statistical matrices, statistical information of the channels, then there is no need to send any signal because the access points send the received pilot signals directly in the centralized operation to the central processing unit. So the central processing unit can compute the long-term statistical information based on these pilot signals in the long term. When we look at the distributed operation, again we will obtain a very similar expression for the frontal signaling plot to the uplink. The central processing unit now sends only the data signals, downlink data signals, because now the access points are responsible to apply the local precoding vectors and adjust the power. So now the number of complex scalars to be shared over the frontal is, again with any precoding, because now the local precoding is applied, in each coherence block is this number. And here, as you recall from the previous parts, this DL is the set of user indices that are served by access point L. So it's the cardinality of this set is the number of users served by access point L, because the amount of downlink data signal is this for each access point L, and we sum over all access point L. So again, we have a very similar expression. Now we continue with the spectral efficiency performance of the downlink centralized operation using the same running example as in the uplink. You see the parameters, and we plot the cumulative distribution function of the spectral efficiency per user. And we recall the overall centralized transmit precoding vectors in this form. And here this bar notation is just for the precoding vectors with arbitrary norm, and we normalize them and apply a power coefficient here. And we consider a new fractional type scalable power allocation and propose in our book. And it's a fractional type power allocation. And this MMSE all corresponds to the MMSE combining vector from the uplink using the uplink downlink duality as a precoder, and all represents the case where each access point serves all the users. So it's not scalable. And the second one, the red one, is also not scalable, although dynamic cooperation clustering is used, because again, we use MMSE, so it's not scalable. But partial MMSE and partial regularized zero forcing from the uplink counterparts are scalable with dynamic cooperation clusters. But now, unlike uplink counterpart, the MMSE all is not the optimal one. So there is no guarantee that it performs better than the others. Interestingly, we see that it has the worst performance among the others. Because although we use a fractional type power allocation, using the power, allocating the power for all the users at each access point is not a good design here. And we see that with dynamic cooperation clustering, MMSE, and also with partial MMSE, we obtain much better performance. And there is a very small gap with partial regularized zero forcing and the other MMSE and PMMSE with dynamic cooperation clusters. Now let's look at the distributed downlink distributed operation. Now using the duality inspired by the duality, again, we use the same combiner structures from the uplink, but as a precoder. And his local MMSE and local partial MMSE. And here, the last two figures represent the scalable alternatives. This maximum ratio precoding and local partial MMSE with dynamic cooperation clusters. Now we use again a fractional power allocation, but now since each access point can adjust its power locally, we use more power coefficients. And again, we have a normalized local precoding vector based on the local channel state information. And here, as in the uplink, this maximum ratio precoding does not have the ability to suppress interference, so it has the worst performance. But unlike uplink counterpart, now local MMSE all, where each access point serves all users, has worse performance than the others. The scalable local partial MMSE and with DCC. And also the gap between the local partial MMSC, the scalable one, and the unscalable local MMSC is very small. Now let's continue with spatial resource allocation for both uplink and downlink operation. And we start with the transmit power optimization, because we will compare our scalable heuristic power control and power allocation schemes with the optimized benchmarks, either to maximize the maximum fairness and or some spectral efficiency. And for uplink, irrespective of the centralized and distributed operation, we have K transmit powers corresponding to each user K. But in the centralized downlink, there are again K transmit powers, because not to destroy the direction of the overall pre-coding vectors, we assign only one power coefficient for each user. But in the distributed downlink, now each access point can adjust its power locally. So we have more power coefficients. The important thing is that even in the optimized case, the same power coefficients are optimized for a given long-term channel statistics. So the same power coefficients are used for multiple coherence blocks as long as the statistics do not change. So no need to change the power control on a coherence block basis. So depending on the channel statistics, based on the choice of combining pre-coding, we can optimize power control and power allocation. Now let's start with the uplink power optimization. In uplink, we call it power control because it corresponds to controlling how much each user K cuts down its maximum power. And we have this constraint, and we collect all the power coefficients in a vector. It's P, K-dimensional vector, and now the effective SNR of each user K has a generic form in both centralized and distributed operation. And you see, as a function of optimization variable P, vector P. And here, Vk is the average channel gain of the desired signal, and this vector Ck is the average channel gains for the interfering signals, and we have an effective noise variance. So this term are actually functions of selected combining schemes and channel statistics, but we have a generic form here. Now, let's look at the first benchmark. Maximum fair spectral efficiency maximization. And the problem is to maximize the minimum spectral efficiency, and we have the transmit power constraints. So it's a fairness, user fairness based optimization criteria. And luckily, it can be solved optimally by a bisection search, as shown in the literature. And in a bisection search, at each iteration, we solve a linear feasibility program. All users at the end will have equal spectral efficiency at the optimal point, and at least one user will use the maximum power. And although the optimal solution is guaranteed, it's not actually a simple scheme using this bisection search. But using this information, we can design a fixed point algorithm. And this fixed point algorithm converges to the global optimal solution, as the bisection search does, but in a very quick way. So using these closed form updates, very simple updates, it converges quickly. But the problem is that since we consider network-wide optimization, the complexity grows with the number of users. As you see, we take the maximum of all power coefficients in this update. Although it's a very simple operation, according to our scalability definition, this algorithm is not scalable, but we will use it as a benchmark, optimized benchmark. And now let's look at the uplink sum spectral efficiency maximization. Now our aim is not to focus on the worst user, because now the fortunate users may cut down their spectral efficiency, but instead we focus on the sum spectral efficiency. Now using the generic form, we have this function, and we actually omit here the pre-log factors and representing the ratio of the channel users, because it doesn't affect the optimality of the problem, and we have the power constraint. And the conventional way to solve this type of sum spectral efficiency maximization problems is the weighted MMSC reformulation. And we use this weighted MMSC reformulation and design a block coordinate descent algorithm. Again, it's not scalable, but for uplink, It has closed form updates, and we show the updates here, but again the complexity grows with the number of users. But again, we will use this algorithm as a benchmark. Now we will continue with the fractional uplink power control, which is a classical heuristic in the multi-user systems. And it creates a balance between the spectral efficiency of the fortunate users, cell-centered users, and unfortunate users, cell-edge users. But in a cell-free network, we have a different situation because now each user has multiple serving access points. And in this work, a fractional power control scheme for cell-free networks is proposed. And now you see in the numerator the total channel gain for user K from each serving access points. So we sum all the channel gains. And there is a normalization factor in the denominator, and we have an exponent tuning parameter for the fractional power control. Not to exceed the Pmax, we have a denominator term here. And when we set this tuning parameter as 0, we obtain the full power, Pmax. Each user uses its full power. So actually there is no power control. When we make it -1, it corresponds to fully compensating for the variations in the total channel gain. If the total channel gain is larger for some particular user, then less power is assigned to that user. So it's actually fairness-based mechanism. So in this work, in this reference, it's recommended to use negative exponents for a good performance. But we can also use a positive exponent, and in this case, we somehow mimic some spectral efficiency maximization since more power is used by the users with good channel conditions. So in an aim to maximize the some spectral efficiency. But unfortunately, this scheme is not scalable according to our definition because you see, in the denominator, we apply this maximum operation over all users. So the complexity grows with the number of users. So in our book, we design a scalable uplink power control inspired by this fractional power control. So we modify it such that the terms in the denominator does not grow with K, and we use one of our previous sets defined in this ways. So this set is correspond to the users that are served by partially the same access points as user K, because the interference term from these users of this set is actually dominant. So we actually replace in this way. And we again do not exceed the Pmax, and we have a scalable uplink power control. Now let's look at some numerical results for the uplink centralized operation first. And we use the same running example and select the partial MMSE combining, which is the best among the scalable alternatives for the uplink. And now you see the spectral efficiency cumulative distribution function for different power control schemes. And full case corresponds to each user uses its full power, and the scalable fractional power control is denoted by FBC, and we use different exponents, positive or negative, and in negative case we emphasize the fairness, and we also use max-min fairness. It's a benchmark, optimized benchmark, the optimal solution, and some spectral efficiency using the block coordinate descent algorithm with weighted MMSE reformulation. And we have some interesting result because when we look at the full case, no power control case, and some spectral efficiency, they almost overlap. Actually, we have tried several initial points and we have observed this fact. But when we use the fractional power control with a negative exponent, we have actually a larger spectral efficiency at the lower tails for the most unfortunate users. But then the question is, why the max-min fairness does not provide more fairness? Actually, it provides, but at the very lower tail, as you can see. It maximizes the worst spectral efficiency, but by compensating the other spectral efficiencies of good users. So its performance is not good enough. So actually, the schemes we suggest is to use either full power to mimic the sum spectral efficiency or fractional power control with a negative exponent, because the positive exponent does not perform well. Now we look at the distributed uplink distributed operation using the same setup and select the best scalable combining schemes. It's the nearly optimal large-scale fading decoding with local partial MMSE combining. And use different power control schemes. Again, full and scalable fractional power control. We have modified according to the initial reference. Max min fairness and some spectral efficiency. These are the network-wide optimized schemes. But now we have actually, again, the same result. For the full case, full PK equals Pmax, and some spectral efficiency, we have almost overlapping results. And again, fractional power control with a negative exponent is actually good to maximize the fairness. Although max min fairness again maximizes the very lower tails, its performance for almost all of the users is not good as the other schemes. After uplink power optimization and some scalable heuristics, now we continue with the downlink power optimization. And in downlink, it's called power allocation because it corresponds to the problem of how to divide the total power raw max at each access point between the different users that are served by this access point. And we have the same per access point power constraints in both centralized and distributed operation, but we will handle these cases separately because in the centralized case, we have a coupled pre-coding vectors as you see. So only there are k-power coefficients, not to destroy the directive pattern of the overall pre-coding vectors. But when it comes to the distributed operation, now since they are designed based on the local channel state information at each access point, there is no coupling of pre-coding. So each access point is free to adjust the power accordingly. So we have more power coefficients here. Here, the cardinality of this MK is the number of access points serving user K, and we sum over all users. And this XL is the transmitted signal from the access point L, as you recall from the previous parts. Let's start with the centralized downlink power optimization. Now, again, as in the uplink, we have k power coefficients, these rows, and we collect them in a vector. Now, the effective SLNR for user K can be written in a generic form. And here, this BK tilde is the average channel gain of the desired signal, and in the denominator, we have the noise variance, and we have the average channel gains for the interfering signals. Again, based on the selected pre-coding schemes and channel statistics, the values of this term change, but the important thing is we have a generic form in terms of the optimization variable rho. And now we are looking at the overall pre-coding vector, normalized, and then adjust its power. And using some other notations, we can express it in this form. So we now consider the parts of these vectors. And now we can express the per access point power constraints at each access point L using these portions of the overall WK bar vector. So we have some coupling per access point power constraints, as you see. Let's start with the max-min fair spectral efficiency maximization for the centralized downlink operation. In fact, we have the same SLNR structure in the generic form with the k power coefficients as in uplink. Only this tilde channel gains and interfering signal gains differ. But we have almost the same optimization algorithms, but we have a difference. Difference is in the power constraints. Now we have one power constraint per access point, different from the uplink counterpart. Also, as you see in the per access point power constraints, this rho k can affect multiple per access point power constraints simultaneously. So there is a coupling. And the max-min fairness optimization problem can be written in this form. So we maximize the minimum SLNR, so minimum spectral efficiency also, subject to the per access point power constraints. And due to the same structure, although the constraints differ, we can design a fixed point algorithm, and it converges to the global optimal solution of this problem with closed form simple updates. So it converges very quickly, but again, the complexity grows with k, as you can see from the denominator, the operations in the denominator. So again, it's not scalable, but it's a very good benchmark for us. And let's continue with the some spectral efficiency maximization. Again, we have a a similar objective function as in the uplink, but the constraints are different. But again, this weighted MMSE reformulation can be utilized for this problem, and a local optimum can be found using a block coordinate descent algorithm. But now, unfortunately, unlike uplink counterpart, we have no closed form updates. And at each iteration of this block coordinate descent algorithm, a quadratically constrained quadratic programming problem should be solved, although it's a convex and numerical solver is needed, and it's not scalable since it's a network-wide optimization, but we will use it as a benchmark. Now we continue with the scalable centralized downlink power allocation. First of all, let's recall that in the centralized operation, the transmit powers of different access points are coupled through the centralized, these normalized precoding vectors. Since the direction of the precoding vectors is important to cancel the interference, we do not want to destroy the direction. So we have a single power coefficient for each user. But the problem is that if one access point, it increases its power allocation to a particular user, then the other access point serving that particular user also need to do the same. But then per access point power constraints may not be satisfied. So let's look at the first alternative, first scalable one. It's network-wide equal power allocation, and rho max is the maximum allowable power for each access point, and tau p, as you recall from the previous parts, is the number of pilot signals. So according to our dynamic cooperation cluster algorithm, each access point serves at most tau p users using this joint pilot assignment and dynamic cooperation cluster formation algorithm. So in this way, each access point power constraint is satisfied, and the computation does not grow with the number of users, so it's scalable. But as you see, it's very simple, so it's equal power allocation. There is another alternative, which is inspired by the fractional type power control in the uplink. And here, we select the power coefficients for each user k as proportional to the total channel gain, and there's an exponent, additional tuning parameter here. And the term inside the parentheses is the total channel gain for user k from each serving access points. And this additional tuning parameter emphasizes different utility functions. When it is 0, then we obtain the network-wide equal power allocation, as we saw in the previous slide. When it is positive, then we somehow mimic the sum spectral efficiency maximization problem. And in this way, more power is allocated to the users with higher total channel gains. Otherwise, when it is negative, then we emphasize the fairness, user fairness. So more power is allocated to the most unfortunate users, to the users with less total channel gain. But there is an important difficulty compared to the uplink counterpart. Now these coefficients, power coefficient, for example, for a particular user k, affects the transmit power of all the access points with these indices. So the access points that serve this user k. So it appears, this rho k appears in multiple per access point power constraints. And here you see the expected norm square of the portion of the normalized precoding vector corresponding to access point L and user k. But we know that defining this omega k parameter, we know that this access point L consumes at most this amount of power for each serving user. And here this omega k is a worst case parameter, so it's the maximum of the portions of the normalized precoding vector portions and the expected norm squares of the portions of the normalized precoding vectors. So here the maximization is over the access point indices that are serving this user k. So we take the maximum of it, and we know that this access point L consumes at most this power. Now we also introduced an additional tuning to our problem. And here kappa, you see the omega k from the previous expression, and there's a kappa parameter, and this kappa parameter is between 0 and 1, and it reshapes the ratio of the power, this proportionality. And what is the motivation? The motivation is that when omega k is too high, for example, when it is close to 1, because it cannot exceed 1, as you see from this expression, because it's the expected norm square of the already normalized precoding vector, portions of the precoding vector, then most of the access points that serve user k will cut down their power, because they will assume that they use much more power than expected. Because you see, the maximum of it is close to 1, but the other portions can be close to 0. So in this case, more power is consumed than the expected. So we introduce an additional parameter to see the effect. And to satisfy the power limit of each access point, it's the rho max. Also, we normalize the power coefficients using this denominator term. There are some details here, and here we skip the details, and in our book you can find the details. But the important thing is that due to this selection, we both normalize it so the power coefficient, power of each access point does not exceed this rho max. And also, due to this special structure, the computational complexity does not grow with the number of users. So it is scalable according to our definition. Now, let's compare the performance of different power allocation schemes for the centralized downlink operation. And we consider partial MMSE precoding. And the equal one is the scalable network-wide equal power allocation. And the other one is our proposed scalable fractional power allocation. And the maximum fairness and some spectral efficiency. These are the optimized schemes according to the network-wide optimization functions. Now we have a different case compared to the uplink. Now the equal power allocation, actually some spectral efficiency, they are different, unlike uplink counterparts. So although equal power allocation emphasizes the most fortunate users, as you can see the higher tails, when you look at the lower tails, most unfortunate users, it does not actually emphasize the fairness. But this fractional power allocation with a selected tuning parameters, properly selected tuning parameters, actually emphasize the fairness, so satisfies the maximum fairness somehow. Actually, for example, here, at this point, it's better than maximum fairness, but it's not actually surprising because maximum fairness, when we look at the very lower tail, it's the best because it maximizes the minimum spectral efficiency in the system. But actually, for almost all other users, there is a spectral efficiency loss for the other users with maximum fairness. But here, this fractional power allocation is advantageous to emphasize fairness. Now let's continue with the distributed downlink power allocation. We are handling it separately because now we have more power coefficients. And to express the optimization problem in a more manageable form, we introduce the square roots of the original power coefficients. And this is just for tractable formulations. Now the effective SANR for user K can be expressed in generic form, but now the structure is a bit complicated than the other ones, uplink and centralized downlink. And here now you see some vectors, collected power coefficients, square root of the power coefficients, and some constant vectors and matrices. These are positive semi-definite matrices based on the selected precoding scheme and channel statistics. These are fixed for the optimization problem. And we look at the normalized local transmit precoding vector, and also its power is adjusted according to this power. And since this tilde rho KL represents the square root of this original power coefficient, we can express in this form. Also, the per access point power constraints is now expressed as convex quadratic constraints for each access point. And let's first start with the maximum fair spectral efficiency maximization. Since now the generic form is a bit more complicated, the previous fixed point algorithm that converges to the optimal solution cannot be used. But there are some other tools, although the complexity is much higher. The maximum fairness optimization problem in the epigraph form, this introduced T, actually corresponds to this epigraph form, and all the SANR should be greater than this T, so we maximize this T. This is the epigraph form of this problem, And we have per access point power constraints. And obviously it is not scalable because it's a network-wide power optimization, but it's a quasi-convex problem. So we can apply bisection search over this T, representing the minimum SANR in the system. And we can find the global optimal solution by solving a sequence of second-order comprogramming problems, which are convex. But we need a numerical solver here. So its complexity is very high, although the global optimal solution is obtained. And the spectral efficiency, some spectral efficiency maximization is the second network-wide power optimization for the distributed downlink. And using the generic form, you see we maximize the summation of the spectral efficiencies by omitting the pre-log factor again. And we have per access point power constraints. Again, this weighted MMSE reformulation can be used, but now a local optimum is guaranteed with block coordinate descent algorithm. But unfortunately, we have no closed form updates. And at each iteration, a convex, quadratically constrained, quadratic programming problem should be solved. And obviously, it is not scalable. But we will use some spectral efficiency and max-min fairness maximization problem solutions as our benchmarks. And what are the scalable distributed downlink power allocation schemes? And we can actually extend the power allocation scheme proposed in this work for arbitrary number of access point antennas and also considering dynamic cooperation clustering. So here we change the denominator to make it scalable and also satisfy the power limit of each access point. So it's a scalable type power allocation and also fractional type. And here it is a predetermined function of the channel statistics. These are the channel statistics matrices. And this function is selected, pre-selected, and it determines the relative importance of transmitting to user I. So we can mimic either some spectral efficiency or max-min fairness, and denominator is just for normalization. For example, when we select this function as 1, then each access point, per access point equal power allocation with these parameters. So it corresponds to equal power allocation. But for example, when we select the channel gain of user I to the access point L and some exponent V, then we have this form. And in the reference work, this exponent is suggested to be taken between 0 and 1. So to emphasize somehow unfortunate users in the coverage area, because it's proportional to the corresponding channel gain. So now let's look at some numerical results for the downlink distributed operation, and we consider again a scalable pre-coding, the best among the other scalable pre-codings. It's the local partial MMSE and the same running example. And now this equal is just corresponds to actually this fractional power allocation, but exponent 0, and positive exponent and negative exponent VC, and also the other optimized schemes, max-min fairness and some spectral efficiency. And first of all, as you see, as also shown, also suggested in the reference work, this negative exponent is not a good idea using a negative exponent with the considered fractional power allocation. So instead, using a positive exponent actually results better performance, much better performance than equal power allocation, VC, for most of the users. And with max-min fairness, now, unlike the other scenarios, now we see the fairness improvements actually clearly, visibly. You now see the minimum spectral efficiency in the system is maximized. And for actually 90% of the users, where the cumulative distribution function is 0.1, is the 90% light spectral efficiency is much higher than the other schemes, but it's not scalable, it's optimized scheme. And also with some spectral efficiency, although the fairness is destroyed at the lower tails, we can actually attain much larger spectral efficiency for the other users. So actually there is a gap between the scalable power allocation, although it's not very big. So some other scalable power allocation schemes can be designed as a feature work. Our final section is the takeaways and open problems part. And what are the takeaways of this tutorial? Cell-Free Massive MIMO attempts to provide almost uniformly good service everywhere in the network area. And we take benefit of massive macro diversity due to the distributed antennas in the coverage area. And it's a very potential beyond 5G or maybe 6G technology in the future. But the interference suppression is very critical, so MMSE processing, MMSE type precoders and combiners should be used in cell-free massive MIMO to outperform both cellular massive MIMO and small cells. And we have presented scalable alternatives for MMSE type processing with dynamic cooperation clusters in this tutorial. We have considered two implementations, centralized and distributed implementations. Centralized implementation is theoretically preferable because we have greater spectral efficiency and also we have less frontal signaling compared to the distributed operation. Of course, here we consider error-free frontal transport network, but in a practical scenario, what is the trade-off between them is an open question. And also, we can employ this centralized cell-free massive MIMO implementation on top of the CRAN architecture, CRAN network architecture, and we can use virtualization in the baseband processing unit. We call it central processing unit. But when it comes to the distributed implementation, in its current form, it's now practically preferable to use this radio stripes concept if we have a serial frontal to make sense. And also the processing complexity is reduced. And because we have simpler combiners and precoders, and also this complexity is shared among the access points. So it's also practically preferable. And the physical layer of cell-free massive MIMO is fairly well understood. But the topic is in very early stage, so there are lots of open problems. First of all, initial access and synchronization, and also you see the other problems, hardware impairments, the considering frontal transport network and also radio site, and also due to the low cost components at the access points, and quantization of the frontal signaling and deployment of the frontal network, and also lack of some other channel models and prototype development. These are some open problems. And we want to thank to our colleagues and collaborators for this tutorial. And also we would like to thank to our funding agencies and supporting our work. Thank you very much for listening us. And if you have any questions, we would be glad to answer them. And you see our book again, the website for our book. And also there is a GitHub folder. And in this folder, you can find our books free PDF and also the codes accompanied them for the numerical results. And thank you very much.